So firstly, if we look at this graph, right, and we assign values to the concentrations. So we have 4 different concentrations. The concentration of the products and reactants in the first equilibrium and the concentration of the products and the reactants in the second equilibrium. So our Kc value, okay, let me write it down here. Our Kc value is the concentration of our over the concentration of our reactants. So for the first reaction, so concentration of our products into O4 is our product, yeah? Okay? So the concentration is 3. And the concentration of our reactant will be 1. Okay, 1. Yes. Okay, so this is the values assigned to it now. Yes. Then this is equal to 3. Then the Kc value for our second equilibrium, we have 6 divided by 2. Well, 2. 6 divided by 2, so it will still give us 3. Okay, so our Kc value remains constant, even if we change the concentration of either the products or the reactants. Okay, so if we look at what we did yesterday, we we increased the concentration of one of our reactants.
Sorry, man.
This is an egg.
It's not an egg. I was ready. Sorry, man. I'm late. We're still busy with the thingies for the open day, and we have to borrow. Where's Orifile? No. Oh yeah, we have to borrow her. So sure, man.
Okay, I am recording the class today, so go watch it.
It's still a concentration thingy.
We're going to move on to temperature. I'm going to start with temperature, but I'll wait for you guys till we get back.
Enough, but thank you, man.
Temperature is the most difficult one of all. Okay, so we'll be behind the class. Okay, because of this open day. Okay, so we increase the concentration of one of our reactants. So, according to Le Chatelier's principle, the system will do whatever it does to oppose what we did. So we increase the concentration of our reactants. So it wants to decrease the concentration of our reactants. How does it do that? By, yes, turning our reactants into more products. Oh no. Yeah.
Oh, it's hello. Yeah.
Go. I'm recording this class. Sorry? Yes. I'll go to it now. Just let me finish these 2 dots. So we increase the concentration of our reactants. So the system wants to decrease this concentration. How does it do that? How does it do that? By turning our reactants into more products. Okay? So the forward reaction is favored. So this concentration of our CO2 will then decrease by reacting with our hydrogen gas. So the production of our products are increased. Then, the second one is if H2SO4 is added to the reaction, okay, that means water will be removed. Okay. Sorry?
For example, you make it easy with values. So when you calculate it, is it going to be values or is it just?
It will be valued.
It's easy.
3 and 1, 6 and 2. Is it a new thing?
No, it's our Kc value.
Yeah, but how do you know which one to?
Okay, I'm going to get to that now. Okay, so if we add HO2 to our reaction mixture, water will be removed. That means if we look at our reaction here, water will be removed. So we are taking away some of our product. Okay? Now the system doesn't want that. It wants to put more product back, so our forward reaction will once again be favored. Okay? Because we, according to Chatelier, we are going to do whatever opposes the change we made. We took out product, so it's going to make more product. Okay, so what they say here then, so more CO2 will react with our hydrogen gas, okay, to supplement the decrease in the concentration of water, and we will increase the yield of the reaction. So we will increase our amount of products.
So if products are taken away, more products will be produced.
Yes.
So what's being added? Reactants.
Nothing is being added. We are decreasing our concentration of one of our products. Yeah, it's instead of increase, then we have decrease. Okay, so this is another thing that can happen. Now we can look at the graphs. I forgot I haven't talked about the graphs with you guys. Okay, so we have two graphs, concentration versus time. Let me just remove these quickly so you can see better. So we have concentration versus time. So in the first one, we increase the concentration of one of the reactants. Okay, so this is our concentration. Our reactants concentration will go down, right, because it's being used to form our product. So our NO2, nitrogen oxide. Nitrogen oxide, okay, is represented by the solid line. And the concentration of N2O4 is represented by the dotted line. Okay, so we, at some point at the start of this reaction, we reached an equilibrium. Then we disturb the equilibrium by increasing the concentration of our reactant. Okay? The Chatelier's principle says a new equilibrium will be reinstated. Okay, so then our reactants react to create more products. So our reactants become less and our products become more. And a new equilibrium is established. Yes. Okay. Yes. Okay, so let me just draw in these lines again. Oh, this is going to go terribly. Okay, so in our first equilibrium, okay, before we added more reactants, we had a concentration of our NO2, so a concentration of our reactant, okay, of 1, and a concentration of our product of 3. So our Kc value, or equilibrium constant, okay, it is the same as, let me write it up here, our Kc value is equal to the concentration of our product over the concentration of our reactants. So our y-axis here shows us the concentration. So these values 1, 2, 3, and 6 is our concentration. At the bottom, when we are in equilibrium, from the pink line, we have a concentration of 1. So we have a concentration of 1 for reactants. At the top, we have a concentration of 3 for our products. That's how we get to this Kc value. So concentration of 3 for our products, a concentration of 1 for our reactants. And we get a Kc value of 3. It is a constant, there is no unit.
The product is the one that started.
It's not a constant, it's a ratio. Sorry.
The one that started is the product.
Yes, it's our product. So N2O4. They write it here as well. N2O4, that's our product. Okay. It's a ratio. It's the ratio of the concentration of the products to the reactants. So it's no units. Okay, we are going to get more specific into the Kc value after we did our 4 different things we can do in a reaction to disturb our equilibrium. Okay, so we're going to do more of the Kc value later. So now we change the concentration of our reactant, so a new equilibrium is established. And if we look at the values of these concentrations, so our NO2, our reactant, will have a concentration of 2, and our products, our blue line, will have a concentration of 6.
So they increase the concentration.
Yes, yeah, we can see they increase the concentration of our reactants, and a new equilibrium is established.
Increase the concentration of the reactants, it decreases what?
No, it increases the amount of products and it decreases the amount of reactants. Okay.
How do you know which one is a reactant and which one is a product?
They will tell you in the equation.
Yes, they will give it to you.
So if they increase the reactant, the reactant decreases, the product will come more.
Yes.
If they increase the products will decrease, and the reactants will come more.
Yes. Okay, because one of the either our forward or backward reaction will be favored. Okay, so this is the second one, our new equilibrium. We have a concentration of products of 6 and our concentration of reactants will be 2. So we have 6 divided by 2, which will give us the same, 3. So our Kc value remains constant. Okay, and in our second graph here, so they give us this reaction here, NO2 gives us N2O4. This is the same as the reaction here. So they say this is the line for N2O4, so that is our product. And the solid line is NO2, that is our reactant. So what concentration did we change here?
The concentration of the reactant still. But
Okay.
it decreased.
Yes, we decreased the reaction. We decreased the concentration of our reactants. Okay. So, if we look here, we have 2 different initial conditions for a forward or reverse reaction to be favored. Okay, so now we removed some of our reactants. We decreased the concentration. And what happened? Okay, so we removed some of the reactants. What does La Chatelier say is going to happen?
Product.
If you remove the reactants, the backward will be fixed.
The backward reaction will be favored by having our products react with one another and form more reactants. Okay, we took away reactants. La Chatelier's principle tells us we don't want that, right? The reaction doesn't want that, so it's going to add more reactants.
So there'll be more products.
Okay, now there will be less products.
Yeah.
What? You just said that.
Yeah, the reverse reaction will be favored. Okay, yes.
So when the products react with one another,
The products will
form
react
form reactants.
to form more reactants.
Yes. Okay, you remember the seesaw? Okay, let's do it as a seesaw. Okay, sorry?
I think the seesaw is a bit confusing.
I understand it's between
Yeah.
Okay, so I'm going to explain the seesaw anyway. So we have our reactants and our products. Okay, so now we removed some of our reactants. So the reactants will become less and the seesaw will be tipped this way. Because we decreased the concentration, so now there's less reactants.
You know what, I don't know why it's confusing. Because doesn't the seesaw go like this if there's more weight on that side?
Yes, I'm wrong. It's like this.
That's why.
Sorry.
Confused.
Okay, so I got confused too apparently. Okay, so we removed some of our reactants. So our reactants weighed less.
Yes.
So it's like this now. So we have now more products, less reactants. So how do we fix it? We use our products to make more reactants. Okay, so we use our products to make more
So the
reactants.
backward reaction is taken.
So the backward reaction is favored. Okay, now let's add it here.
So which of the products decreased in order for the reactants to increase?
Yes.
And be equal to-
Yes, so you can see that on the graph. So we just said our products must react more to increase our or concentration of reactants if we remove some of the reactants, right? Okay, so our products is used so their concentration will become lower. To make more reactants, so our reactants concentration will become higher.
So what if there was more reactant than products?
So you're saying, what if the graph looked like this? For example, if this was our product, our reactants concentration. Okay, nothing will happen. Okay, just because they do cross over doesn't mean that they have to cross over.
In terms of the seesaw, like if the reactants were
If we increase, do we increase the number of reactants?
From the beginning, it's already like this. That's what it is. It's impossible because it has to be equilibrium.
Yeah, so this is what we have at the beginning. And then at some point the reaction will go on and create an equilibrium. It will reach that equilibrium. Do you understand?
Is it your question?
no.
Okay.
That's not my question.
Okay, so what's your question?
The seesaw,
Yes.
this is the product, this is the reactant, but the seesaw is like this. So how
Yes.
do you make it like equal? How do you make it equal?
By a forward
Okay.
reaction.
By taking the by taking some of the products
Reacting some of that to create more of this one.
Yeah.
So if you create here,
it will way more.
Okay, good, you understand? Okay, amazing. So just to add it to here, because now our table only says increase, right? But what happens if we decrease? Okay, so if we, no, let me write it in blue. Okay, so if we decrease the products, our forward reaction will also be favored, right? Because we removed some of the products, we want to put more product back. How does that happen? By favoring the forward reaction. And then if we...
Yeah, but you were talking about the
No.
Decreasing the products to increase the reactants.
So if we decrease products, it's the same as increasing the reactants.
Yes.
Okay.
Okay, and if we decrease
The reaction.
the reactants,
The reverse. Oh, because now the bad thing has to work to get this one.
yes, so our reverse reaction is favored. Okay. Now, I'm hoping I don't confuse you further. Okay, when we look at our last graph, let's do it in green and brown.
The rate of rate versus.
The rate versus time.
That makes sense because when it's going up, you can see the graph shifting up. When it's decreasing, it's shifting down.
Yes. But the solid line and the dotted line do not represent our reactants and our products. It represents our forward reaction and our backwards reaction. Okay, so the solid line represents our forward reaction. Okay, so our forward reaction. Yes. Okay, and our dotted line will represent the backwards reaction.
Why are you green my DD? Say you know not doing it to you. Say it. Say it, man.
I'm not your friend.
Okay, let's just highlight this part as well.
Yes, my dear, talk to it.
So these graphs are not that complicated, right? Okay, here we see, okay, the one reaction as a sudden spike in our reaction rate, and then a new equilibrium is established. And it will be the forward reaction because we increase the concentration of a reactant. So if we increase, let's look at this. If we increase a reactant, the forward reaction is favored. Okay? So there will be a sudden jump in the rate of our forward reaction before it reaches a new equilibrium. Same. Okay. So we have an increase in concentration of a reactant. If we look at our table, if we increase our reactant, okay, the forward reaction is favored. Our forward reaction is our green reaction. Okay, so we can see there's a sudden jump in the rates of the reaction, right? Because there are now more NO2 to react with it. Okay, and then we will reach a new equilibrium. That's that. That's it for this graph. So it's not that much more complicated. The most complicated thing is to realize one of these lines represents the forward reaction and the other one the backwards reaction.
If it's a reaction rate, it represents forward and backward.
Yes.
Concentration.
It represents products and reactants. Okay, and the same will happen here, where we decrease the concentration of one of the reactants. Okay, there will be a drop in the rate of the reaction. Okay, and a new equilibrium will be established. Not that bad, right? This one. Okay, so we decrease the concentration of the reactant. So let's see what happens. If we decrease our reactant, our reverse reaction is favored. Okay, so first of all,
Okay, wait. You decrease reactants to, so if we decreasing the
reverse
reactants,
reaction.
the products will make more too. So it's the backwards reaction.
yes. Okay. So we decrease the concentration of one of the reactants. Okay. So of course there's less reactants now to create products. Okay. So we will have a slower reaction rate. Okay. That's why it drops down. Okay. And then it just goes on and forms a new equilibrium.
So now to get this straight then, so if we have our seesaw, right, we have our reactants and our products, and then but we have like less product, less reactants, we're going to take our products and like to here.
Yeah, turn them into reactants. Yeah.
The same thing with the thing here. The same thing to increase the products with the reactants.
Yes.
You know what? To me, there's nothing like this with the increase. No, the decrease one. And
Yeah.
this one with the increase. No,
Ye-
you did it the other way around.
Yeah. I was wrong. I'm sorry. Okay. I apologize for that. Okay. So I'm just going to this is the concentration. What happens with concentration? So I'm just going to intro you guys to temperature. Okay. We won't do much work on it because we have so many people missing due to the open day. Yes. So when you get this in a test, let me see. Okay, this is the Afrikaans version. I still need to open the English version. But for example, they give you a graph and they give you this. What does this mean? Exothermic. Okay, so now we are talking about our temperatures. No, still the wrong one. This one. We are talking about our temperatures. Right? So we are going to talk about exo and endothermic reactions. So if they give us this in a reaction, right, delta H is smaller than 0. Okay? It's an exothermic reaction, first of all. but it is a forward reaction that will be exothermic. A backwards reaction will be endothermic.
Because it uses more energy. And that other one gives away.
Yes.
No, exo gives away.
Exo gives away, yes.
Okay, so the forward one
The forward one is this one,
exo.
exothermic. The backwards one will be endothermic. Okay, you understand that? Simple enough to remember. So now we don't have a nice table with rules that tells us the forward reaction is going to be favored or the backwards reaction is going to be favored. It tells us if there's an increase in temperature. If you hear increase in temperature, what do you think? Exo or endo? Exothermic, yes, okay. Okay, so if we increase the temperature of our reaction mixture, okay, you increase temperature, you think of exothermic, okay. If you think, okay, now the exothermic reaction will be happy because there's more heat, okay. Le Chatelier's principle tells us then the opposite will happen to establish a new equilibrium, so it will favor a endothermic reaction to decrease our temperature. Okay, so we'll try that again.
Yes.
Okay, if we add heat to something, you think exothermic, okay? Because if there's heat, you think exothermic. Okay, more temperature, exothermic. Okay, so Le Chatelier's principle tells us, okay, we want to oppose the change we just made. Okay, so we added more heat. Okay, so it's like we. Okay, yeah. So let me rather say. So we increase the heat. Okay, what Le Chatelier says, we want to oppose that. How do we do that? By taking that heat and turning it in and using our endothermic reaction. Okay, so increase in temperature, the endothermic reaction will be favored. Okay, if we decrease our temperature, our exothermic reaction will be favored. Okay, but this will be different for each reaction because if we look here, we can see this is an exothermic reaction. So that means our forward reaction is exothermic. But here we have an endothermic. So still our forward reaction is endothermic now.
So whatever it is we're given first, that we'll see there, will be the forward one.
Will be the forward reaction, yes.
Whatever we do, this will be the backward.
Yes. Okay. So it is important to remember that the delta H they give us is for our forward reaction. Okay. If we heat it up, the endothermic reaction will be favored. And if we cool it down, the exothermic will be favored. Okay, so but that's all I'm going to do with temperature now. Okay, because there's a lot of people missing in temperature.